Okay, so let's talk about systematic and random error. So if you remember back to Module 1, there we said we had descriptions of systematic and random errors in Module 1, and we said then that systematic and random errors are better done using statistics later in the semester. So that's where we are. We're later in the semester. We know a lot about statistics now, so we're going to use those statistical techniques to calculate the systematic and the random error in a measurement. So using statistics, we're moving into Chapter 7, and we have systematic uncertainty, which we use the letter B for. So B for bias, that's systematic, and the random uncertainty is P here. P for precision. So if we combine the systematic and the random error together, we get what we're calling now total uncertainty. So total uncertainty, in this class, if you see a problem using total uncertainty, that particular term, total uncertainty, that means use the examples in Chapter 7 to solve this problem. So that's a tell for something like a final exam. So when we have the systematic uncertainty and the random uncertainty, we can combine them together using propagation of error techniques, using the root of the sum of the squares, and find the total uncertainty. So our goal now is to find the systematic and random uncertainties to combine to the total. So for P, starting with the random uncertainty, we can use our equations from Chapter 6 to find the uncertainty in the mean. So we take a bunch of measurements, we find the standard deviation, and for our n value, we can find the student's t coefficient and find the uncertainty in the mean, which we're calling p x bar, for x bar is the mean. So this is, again, a Chapter 6 calculation. We've been doing this already. And the standard deviation of the mean is different than from the standard deviation of the sample. And so we call S x bar Sx divided by the square root of n. Again, that's from the previous chapter using the central limit theorem. So these will come up in the total uncertainty calculations. We often want to know, given our measurement system, what's the uncertainty in a single measurement? I'm going to take a measurement. What's my uncertainty in that measurement? And so the way we do this is we do an experiment to find the statistics. So we take many measurements of the same thing, and we can use those statistics to predict the uncertainty in the mean of the measurement. We've already done that. But we can also use those statistics to predict the uncertainty in a single measurement or in a few measurements, 2 measurements or 3 measurements, the mean of 2 measurements. We can reuse the statistics. So we do a big experiment, we rent equipment, we get the data, and then we can use that going forward. So we use the standard deviation from our experiment, and we use the student's t that goes along with that experiment. So the uncertainty in the mean, again, this is what we've been using with the student's t and the standard deviation from our experiment and the n of our experiment. If we want to find the uncertainty in the mean of a few measurements, where a few is now m, we reuse the student's t, reuse the standard deviation, and divide by the square root of m. And in the book they call that p x bar f. And then this is the more common case where we want the uncertainty in a single measurement. That's just using m equals 1, and so we're dividing by the square root of 1, and so it comes out to plus or minus t, again reusing that student's t and multiplying by the standard deviation from our experiment. So we do one experiment, we reuse those statistics to predict the uncertainty in other measurements. There's a common case that shows up when we're doing the uncertainty in a single measurement. The random uncertainty in a single measurement is p. So if we have m equals 1, then we know that the uncertainty in a single measurement, px here, is plus or minus t times sx. A common case is if we have 95% confidence level, and our original experiment where we generated the statistics had a large n, greater than 30. If we use those two parameters, that gives us a t of about 2. And so if we're happy with a confidence level of 95% and our original experiment that gives us the statistics has n greater than 30, then the uncertainty in a single measurement is twice the standard deviation. So this 2 times Sx shows up in different places when you're doing uncertainty calculations, and that's where it comes from. It's the uncertainty in a single measurement, assuming 95% confidence, and assuming that the experiment with our statistics had an n of greater than 30. So for total uncertainty, we need both B, remember B is the systematic, and we need P, the random uncertainty, and we combine them together for the total uncertainty. So for B, we generally, in this class, get that just from the sensor specification. So generally we're given the accuracy as a percentage of the full-scale span. And P we calculate using the statistics, and we combine them for the total uncertainty. Uncertainty in a single measurement, again we're going to get B from the sensor specifications as a percentage of the full-scale span. P now has T times Sx. We're not dividing by the square root of n because we're using a single measurement, so we would divide by 1, and we combine those together for the total uncertainty. So we might be asked for the total uncertainty in the mean, or the total uncertainty in a single measurement, or sometimes the total uncertainty in a few measurements, and that's how we differentiate. So here's an example that combines everything together. So we're manufacturing plastic pipes. This is from the textbook. And we have a scale with the accuracy of 1.5% of its range of 5 kilograms. And we measure 10 parts and find their mass, and this is the listing. And so we're supposed to find the mean of the sample, the standard deviation of the sample, and the standard deviation of the mean, the total uncertainty of the mass of a single measurement with 95% confidence, and the total uncertainty of the mean with 95% confidence. So these are really not difficult to calculate, but you really have to understand the terminology, what total uncertainty of a single measurement or the mean, those kinds of things can trip people up. So the first two are just statistical calculations that we've done before. So find the mean, add them all up and divide by n, we get 1.94 kilograms. For the standard deviation, we're adding up all of the deviations and using the usual equation to find 1.65 times 10 to the negative 2 kilograms. That's the sample standard deviation. And then the standard deviation of the mean is just the standard deviation of the sample divided by the square root of n. So n here is 10, so we get this number. When we're looking at C and D doing the total uncertainty, I would actually usually calculate the total uncertainty in the mean first, because that's what we've been doing for chapter 6 the most. So in the mean, we have T S divided by the square root of n, which is the S of the mean. We need the T from the student's T table. We have n of 10, so V is 9, and 95% confidence level, so we get a T of 2.262. Use that same T times the standard deviation of the mean, and we find P for the mean. B is always going to be our 1.5% times the range. That gives us 0.075 kilograms. In both cases, we use the same thing. So for the uncertainty in the mean, this is our usual calculation, and we combine them for the total uncertainty in the mean, 0.076. Total uncertainty in a single measurement uses P for single and the same B, and we get 0.084. So a little bit higher uncertainty in a single measurement, where if we take 10 and average, we're at a little less uncertain. Okay, so just a reminder of the terminology we're using here. Total uncertainty, if you see that on a problem, chapter 7. Back in Module 1, we promised that systematic and random errors would be done doing statistics. That's Chapter 7 here and uses concepts from Chapter 6. So total uncertainty means Chapter 7. Systematic uncertainty we're calling B. Random uncertainty we're calling P, for bias and precision respectively. So just keep track of all of the terminology because they sound very similar and it's easy to get them confused. All right, so if you are confused, let me know if you have any questions. Otherwise, I will see you in the next lecture.